Hello viewers, welcome to the course of mechanics. This course is suitable for the students who are doing undergraduate study in physics in various Indian universities. The content of this course can be found in the description of this video. The objective of this course is to develop the tools which will help us to observe, analyze, and explain the physical phenomena happening around us. Events as simple as stopping a car by applying some brake is associated with various physical quantities like velocity, acceleration or deceleration, force of friction, and the list goes on. In our daily life, we often neglect various interesting observations, considering them as trivial. For example, here in India, when we try to discharge some amount of water through wash basin, water tends to circulate in a counterclockwise direction around the outlet of the basin. Why in a counterclockwise direction and not in a clockwise direction? In this course, we will try to find out the causes behind this kind of interesting observations happening around us. More importantly, we will prepare ourselves to be able to explain even complex phenomena with simpler approach. Now coming to the prerequisite of this course, one should have basic understanding of mathematics, including trigonometry, coordinate geometry, and elementary calculus. Knowledge about vector algebra is a plus. The books one can follow along with this course are Mechanics, Oscillations and Properties of Matter, written by J.C. Upadhyay, Feynman's Lectures on Physics, Volume 1, Introduction to Mechanics by Kleppner and Kolenko, and finally Mechanics by D.S. Mathur. So let's begin this course with the concept of rest and motion. Here I have mentioned certain key points related to the concept of rest and motion. As far as the definition is concerned, if an object over time do not change its position with respect to surrounding, then the object is said to be in rest. And if it does change its position with respect to surrounding, then the object is said to be in motion. Physics is a quantitative subject. It means we must develop the tools which will help us to quantify any observation. For this case of rest and motion, let us consider an example. Suppose we have an observer who is observing the distance of a car with respect to his own position over time. At initial instant, that is time t equal to 0, he finds the distance of the car is around 5 meters. So I am noting down a table how the observation will be made. So at time t equal to 0, the distance was around 5 meters. Then at 1 second, let us consider he found the measurement of the distance around 10 meters. At 2 seconds, it is around 15. At 3 seconds, it was still at 15. Then at 4th second, 20, 5th second, 25, and 10th second, it was still at a distance of 25 meters from the observer. Now if we plot a graph for this set of observation and we place time along the horizontal axis and distance along the vertical axis, the graph will look like if we plot it, what we will get? At 0, the car was at 5-meter distance. Then at 1 second it is at 10-meter distance. At 2 seconds it is at 15-meter distance. At 3 seconds it still remain at the same distance. At 4th it moved to 20. At 5th it moved to 25. And finally at 10th it still remained at 25. So if I join these points, roughly the curve will look like this. From this curve, what we can infer? We can infer clearly that the object was moving in between up to 0 to 2 seconds, and then again it started to move in between 3 to 5 seconds, whereas the object was at rest in between 2 to 3 seconds and from 5 to 10 seconds. So this is how we can visualize the graph of rest and motion. The inferences we have drawn from this plot heavily depends on the observer. For example, the observer could have made the measurements in one occasion from the rear end of the car and in other occasion from the front end of the car. This is a very common error which is related to this kind of extended objects. Let me take a detour and introduce the concept of point object so that we can even make our observations more precise. As far as the definition of point object is concerned, a point object should be dimensionless and should have finite mass. However, in real life, having something is not possible. So, the definition of point object varies from case to case. For example, when a train travels in between New Delhi to Kolkata, the train can be considered as a point object. However, when it is standing on a platform, the train cannot be considered as a point object. It is considered as an extended object. Extended objects are made of huge number of point objects. So in this case, if a particular point is focused or marked, in that case, the distance between the observer and the particular point will always be fixed. So our measurement will be more precise. In rest and motion, we often come across the term absolute and relative. If we can compare the state of an object with respect to a point which is truly stationary, then the state of the object is going to be absolute. However, in this universe, we do not have any such point which is truly stationary. Hence, all the observations related to rest and motion are relative to the observer and depends on surrounding. In the definition of rest and motion, we have emphasized on the term surrounding. Let us take an example to clarify on this term. Suppose a person is traveling in a train which is moving uniformly. To that person, everything inside the train is stationary. However, to the person who is standing outside, the whole train is moving. This means the term surrounding changes the perspective of rest and motion. This term surrounding also brings the concept of frame of reference to this discussion. A frame of reference is a system of uniquely chosen coordinate axes along with standard unit of measurement. It helps us to locate the position of a point. Generally, we use Cartesian coordinate-based frame of reference. However, based on our requirement, we also use plane polar coordinate system, cylindrical coordinate system, spherical polar coordinate system. Among them, Cartesian coordinate system is based on three-dimensional model. However, plane polar is a two-dimensional coordinate system and cylindrical and spherical both are three-dimensional coordinate system. Now we will discuss how can we represent the position of a point in Cartesian and other coordinate systems, and we will try to interrelate the coordinate system with one another. In Cartesian coordinate-based frame of reference, we represent the position of a point by joining a vector from the origin to the point itself. Using the concepts of vector algebra, we can represent this vector r in terms of these coordinate points. Here, I cap, j cap, k cap are the unit vectors corresponding to x-axis, y-axis and z-axis respectively, and x, y and z are the coordinates for this point P. Now let's move on to plane polar frame of reference. In plane polar frame of reference, the position of a point is represented with the length joining the origin and the point itself and the angle this straight line makes with the horizontal axis. The equivalent representation in Cartesian coordinate system for the same point is also shown here. Now using geometry, we can represent or find a relation between this r theta and xy. So x can be represented as r cos theta and y can be represented as r sin theta. If we square both these equations and add them up, we can also find the reverse relation. Again, if I divide this equation by this equation, we can get the relation between theta and xy. So this is how we can represent the coordinate of plane polar coordinate system into Cartesian coordinate system. This plane polar coordinate system is useful for the representation where the motion is confined in a plane. In cylindrical frame of reference, the location of the point can be represented with the coordinates rho, phi and z. The equivalent representation of the same point is also shown here for Cartesian coordinate system. Here, rho is the projection of the line joining origin to the point on the horizontal plane, and phi is the angle between the projection and the x-axis. We can find out the relation between rho, phi and z with x, y, z as follows. Now let's square these two equations and add them. Again, from this set of equation, we can also express phi in terms of x and y. If the motion of a point is confined on the surface of the cylinder, then this kind of frame of reference is very much useful. In spherical polar frame of reference, the location of a point is represented with the coordinates r, theta and phi. The equivalent representation of the same point in Cartesian coordinate system is also shown. Here r represents the radial vector joining the origin and the point itself. Theta is the angle between the radial vector and the z-axis. And phi is the angle between the projection of this radial vector on the horizontal plane and x-axis. We can relate this set of coordinates with this set of coordinates by this following equations. Now, if we square all these three equations and add them together, we can get the reverse relation. Now let's square these two equations and add them first. Now let's divide this equation with this equation. This is how we can represent theta in terms of various Cartesian coordinates. Now if I divide this equation by this equation, we can represent phi in terms of y by x. So let me write them now together. Suppose the position of a point is changing over the surface of a sphere. In that case, this kind of coordinate system is very much helpful. The informations which we have just derived will be very much helpful when we are going to derive the expression for components of velocity and acceleration in different frame of references. Now, so far from this discussion, we must have realized that the state of an object's rest and motion is very much dependent on frame of reference. In the next example, we are going to see how the trajectory is also very much dependent on frame of reference. In this example, we are going to observe the trajectory of water thrown from a helicopter on a wildfire. And the observations are made by two observers. One is with the helicopter, another one is standing on the ground. Here I have drawn the schematic for this problem and I have mentioned the chosen coordinate axis and initial condition. Now after time t from the release of water, the new coordinate of this water is going to be, here you have used the equation s equal to ut plus half at square formula. And this negative sign is arising due to the motion of the water is downward, whereas our chosen y-axis is on the upward direction. Now from the viewpoint of the observer who is sitting inside the helicopter, let me call him observer number 1. His location after the same time interval is going to become, because he is not going to experience any downward motion. So the apparent trajectory of water from the viewpoint of this observer 1 is going to be, as there is no vertical component of motion, the observer sitting in the helicopter will find that the water is only moving downwards. So the trajectory of water is going to become a linear trajectory. Now let's move on to the observer who is standing on earth and he is stationary. After time t, his position is going to be, and the apparent trajectory of water from the viewpoint of this observer is going to become. Now if we replace the value of t from this equation and into this equation, we can write down y in terms of x as. Clearly, this is the equation of a parabola. So, from the viewpoint of observer 2, the trajectory of fall of water is going to become a parabolic trajectory. Now let us see these two things happening in real life examples. In this first clip, the camera is locked on the helicopter. We can clearly see the trajectory of water falling down is a linear trajectory. In this clip, the camera is locked with the surrounding. Here we can clearly see the water is following parabolic trajectory. Now we are going to study an interesting topic where the state of an object will be analyzed from two different frame of references simultaneously. Here, position vector of point P is represented by two position vectors r and r prime with respect to frame of references s and s prime simultaneously. Capital R represents the position vector of origin of the second frame of reference with respect to first frame of reference. Now applying vector algebra, we can write down. In the first case, let us consider the frame of reference S prime is stationary. So in that case, R is not going to change. So if we differentiate this equation with respect to time, we are going to get. Now if we differentiate this equation once again with respect to time, we are going to get. This is nothing but the acceleration of point P with respect to frame of reference S prime and S. Now if we consider the mass of point P is m and we multiply m on both the sides of these equations, this equation is nothing but force equation. It means the force on both the frame of references measured simultaneously is going to be the same. Now let us consider the frame of reference S prime is moving with some velocity v, and this movement is a translational movement. In that case, this r is also going to be a time dependent factor. So we can write down r as a function of t as. If we replace this equation over here, we will get. Now let us differentiate this equation with respect to time. Now if we consider this velocity is a uniform velocity and it do not change over time, then if we differentiate this equation once again, then we can get. This is nothing but the acceleration experienced by the point P from both the reference frames, and if we compare these two equations, they are same, which means if we multiply this with mass m, we will get the force equations. The conclusion we can draw from this discussion is that if one frame of reference is moving with uniform velocity with respect to another frame of reference, then the form of force remains exactly the same in both the frame of reference. This brings us to the concept of inertial frame of reference, where the measurements of force is independent whether the frame of reference is moving or it is truly stationary. Now what if this frame of reference is also accelerating? In that case, another term will be added to this equation. Now we can write down If we differentiate this equation with respect to time successively, we will get. Now if we multiply mass in this equation, so we can finally obtain. This expression suggests that though the observer in frame of reference S and S1 has measured the forces perfectly, still there will be some amount of error in this calculation, and this is arising because of this accelerated nature of the frame of reference. In this regard, we have to remember that rotational motion is having some acceleration always associated to it. So, if this frame S prime is having some rotational movement, in that case this term will always be present there and they will have some difference in the final form of force. Frame of references moving with uniform velocity brings the concept of inertial frame of reference, whereas this accelerated frame of references brings the concept of non-inertial frame of reference.